Imagine I'm walking in Minecraft and I want to get to a block all the way on the other side of this rectangular soul sand area. The rectangle is 15 meters long and 4 meters wide. I walk at a speed of 5 meters per second on the normal grass, but when I go onto the soul sand, I slow down to a speed of 3 meters per second. So the question is, when should I cut into the soul sand relative to this point to ensure the shortest time? This is one of the most common problems under the infamous optimization unit in calculus, and is what I'm here to help with today. So first, what is optimization? It's the process of finding the maximum or minimum value of a function. Basically, you're finding the optimal value for a result of some kind. Whether it be maximizing volume for the least surface area, or like the question I just showed you, finding the optimal time for some sort of operation, this is what optimization is about. Optimization has 3 distinct steps. First, identifying the problem and setting up the equation, then finding the minimum or maximum of the equation, and then checking for endpoints and verifying the answer. By far, the hardest step is the first one, setting up and identifying the problem, so let's figure that one out first. Optimization will always have 2 variables. The variable you want to optimize, and the variable you will change for that optimal value to occur. So in the case of the first question I gave, the variable that we want to optimize is time, and the value that we can change is the distance from this point that we traveled to before entering the soul sand. For other questions, like maximizing volume for least surface area, the value we are optimizing is volume, and the variable we change is surface area. Knowing this helps a ton because the variable we are optimizing, like the time or the volume, is the y value, or the function itself. The variable we are changing is the x value. This means that the optimizing variable, or the y value, will most likely be alone on one side of the equation, while everything else is put on the other side. Now for the other side with the x value, constructing the equation really comes down to practice. But the most important piece of advice I can give to building the equation is that everything in an optimization problem will relate to this x value. Everything will fall under the x value. So let's apply this to the first problem that I gave. We identified that the optimizing variable is time, or t as we're going to call it from now, and that this distance is the changing variable, or x. Let's look at some possible routes. If x is 15, or the maximum, I'm walking directly towards the object through the soul sand. There is no time that I'm on the grass. That makes the distance the square root of 15 squared plus 4 squared meters. The velocity I have the whole time is 3 meters per second. So the time would be distance divided by velocity, or the square root of 15 squared plus 4 squared divided by 3. Now let's look at the other extreme, when x is 0. I walk all the way to the end and walk through the soul sand from there. This time, the time spent is split into my time in the soul sand and my time on the grass. My time in the grass, which is 15 meters divided by 5 meters per second, then my time in the soul sand, which is 4 meters divided by 3 meters per second. So it's clear from these 2 example runs that the time spent is split into my time in the soul sand and my time in the grass. Since velocity is constant in both, we just have to find the amount of distance each route has relative to the x value. So let's say I cut into the soul sand at x distance right here. And from here we already have the first half of the route figured out. Since our distance in the grass is the total length minus x, or 15 minus x, and the velocity is 5, we can figure out that the time spent in the grass will equal 15 minus x all divided by 5. Once I enter the soul sand, my path will be the hypotenuse of a right angled triangle. The width side will always be 4 meters, and the length side will be x. This results in our soul sand distance being the square root of x squared plus 4 squared. Now we divide this by the velocity, 3 meters per second, to get the time we spend in the soul sand. With these 2 terms, we add them up to get the total time spent. Now this is our final equation, and this marks the end of the first step and we get into the actual optimization. So now that we have our equation with the time isolated and the x value figured out, we have to find the minimum of the equation. Now the minimum or a maximum of an equation will always occur at its critical point, or when the derivative equals 0. This is because the graph turns around at that point when the derivative equals 0, and the peak will always occur at that point. So when the derivative is equal to 0 at that point, you can assume that it's a minimum, a maximum, or in special cases it's a plateau point. But you don't have to worry about that until we get into our last step. So this next step involves us taking the derivative of these two terms, starting with the big term. 1/3 is a constant, so we can ignore that for now. The derivative of a square root is 1 divided by the square root of x squared plus 16 times 2. And then the chain rule gives us 2x on the numerator as well. So our final term after we cancel out the 2 gives us this. We then take the derivative of 15 minus x divided by 5, which would be 1/5 but becomes negative 1/5 due to the chain rule and negative x being there. Now since the derivative of time must equal 0 to find the minimum, we take this equation and set it equal to 0. So whatever x value we get from this equation will be the critical points of the equation. From there we can add 1/5 to both sides, then multiply the square root on both sides to get this. Now to get rid of the square root, we're going to square both sides. X becomes x squared, and the other side becomes 9 divided by 25 times x squared plus 16. We then distribute 9 divided by 25, and we get 9 divided by 25 x squared plus 144 divided by 25. To simplify this, I'm going to multiply both sides by 25, and so now we have 25x squared equals 9x squared plus 144. Now we subtract the x squared terms to get 16x squared equals 144. And by dividing 16 on both sides, we get x squared equals 9. And then we square root it to get a total of x equals 3. So now we know the best point to go in is at the x equals 3 mark, minimizing our time. This is our critical point, it'll minimize our time, and step 2 is finished. Now for the last step. If you've made it here, you're in the home stretch and there's just 2 more things you want to check for. The endpoints and our actual point. Let's start with our actual point, the x equals 3 point we found. By setting the derivative to 0, that is actually not a sufficient way of proving that our point was a minimum. It could be a maximum or a plateau point, as I said before. So we must check another way, either through a second derivative or checking the points around it. For now, I'll just be checking the points around the derivative since taking the derivative again is kind of annoying. So choose any point smaller than x equals 3, I'll choose x equals 0, and I'm going to plug it into the t prime equation we had, and it comes out to be negative 0.2. Now for any point bigger than x equals 3, I'll choose x equals 4, and I'll plug it into the t derivative equation, and that gives me t prime equals 0.0357. So since t prime is negative before x equals 3 and positive after x equals 3, we can conclude that is a minimum, since t is decreasing before x equals 3 and increasing after. Now for other examples, the derivative would be positive before your point and negative afterward since it's increasing and decreasing, and then for a plateau point it would either be both positive before and after or both negative before and after. For the very last step, we have to check for the endpoints. This is because endpoints do not have a derivative of 0, but very well may be lower than the minimum or higher than the maximum. Take this graph for example. We can see that the endpoint here is actually the lowest of the graph. It's actually lower than the minimum, but we'll never see it because the derivative of that point is not 0. So that would actually be the correct answer. So to prevent this from happening, we just have to check the endpoints and compare it to our solution. When we cut into the soul sand at x equals 3, the total time is 4.07 seconds. I did this by just plugging in the x equals 3 into the original t equation. So now when we compare it to the endpoints, which we have actually already done from earlier, when x equals 0, we walk 15 meters on grass, giving us 3 seconds plus the time on the soul sand, which is 4 meters divided by 3 meters per second, giving us 3 plus 4 divided by 3 as our total time. This is bigger than 4.07, so therefore is not the solution. The other endpoint is when we just walk through the soul sand, which is the square root of 15 squared plus 4 squared as the distance divided by 3. This gives us about 5.1, which is a lot bigger than 4.07, so our solution comes out to be x equals 3. So that's the whole process. It's a very long process, I know, and that's part of the reason why optimization is so difficult. But as long as you follow the 3 steps, forming the equation with the changing value, then setting the derivative of the optimizing value to 0, and then solving, and then checking the endpoints and verifying your own solution, you should be golden. This is all about practice, so best of luck with future studies, and bye bye.